The electric field is defined as the force per unit charge. It is frequently represented by lines of force originating on positive charges, ending on negative charges, and pointing in the direction of electrical force on a positive test charge. The density of the field lines at a given point is proportional to the strength of the field at that location. Electric potential, also known as voltage, is defined as the electric potential energy per unit charge at some point in space. By analogy with the altitude lines of a topographical map, we can imagine lines of constant electric potential encircling some point of high voltage and forming equipotential lines. These equipotential lines are shown in the figure at the lower left as dashed red lines stepping their way down from high potential near the positive charge to low potential near the negative charge. No work is required to propel a charge around one of those red lines. However, when a positive charge is released, it will experience a force in the direction of the solid black arrows. The arrowed lines represent the electric field in the space between the positive and negative charges. At all points, the electric field is perpendicular to the red equipotential lines. Just as by looking at a topographical map, you can spot the cliff by finding the place where the altitude changes rapidly, the electric field will be large wherever the voltage changes rapidly. Thus, the electric field is equal to the rate of change of voltage with distance. When we construct parallel lines or parallel plates of opposite charge, the equipotential lines step down at a steady rate from high voltage, where the positive charges are, to low voltage where the negative charges are located. The electric field between the parallel plates is constant in strength and directed away from the positive charges toward the negative charges. In hiking terms, this is the equivalent to a long straight cliff. Note that at the ends of the lines, equipotential lines flare outward and the electric field bulges. The equipment for this experiment includes a voltage source, seen in the upper right-hand corner, and set for 10 volts. A voltmeter, upper left, with the common hole connected to the 0 volt side of the voltage source. The red input to the voltmeter is equipped with a relatively sharp-ended probe for sampling the voltage at any point. The dial on the voltmeter should be at the 20 volt maximum setting. The long straight conductors are placed parallel to each other and in contact with semiconducting paper. Plus 10 volts is attached to one of the conductors and 0 volts is attached to the other conductor. The conducting paper allows a trickle of current to flow through. If you're fortunate, your lab TA will have already put the semiconducting paper in place with the conducting bars. Otherwise, you'll need to carefully punch holes in the paper for the screws to pass through. If you consider the marks on the paper like XY coordinates, the holes are placed at the points 4, 4, 4, minus 4, minus 4, 4, and minus 4, minus 4. After making small starter holes at each of the 4 points, carefully push the screws through each hole in the paper. Place the connecting bars in contact with the paper and use the wing nuts to make the contact solid. As you'll see, we neglected to screw one of the nuts tight enough when we were constructing ours, and this led to later problems. With our 2 conducting strips screwed firmly in place, we connect the common input of the voltmeter to one of the strips using the alligator clip. Then connect the high voltage output of the voltage source to the other strip. Turn on the voltage source and adjust the output to approximately 10 volts using the coarse adjustment knob. Then use the red voltmeter probe to first check the voltage at the low end, which should read 0 volts, and then check the voltage at the high end. If the high end voltage is not exactly 10 volts, then turn the fine adjustment knob on the voltage source until it is 10 volts. Firmly touch the probe to the center line on the semiconducting paper. The reading should be approximately 5 volts. Notice here we got a reading somewhat less than 5 volts because we had not screwed one of the wing nuts tightly. Use the red probe to find a point on the paper near the 0-volt conductor with a voltage of precisely 2.0 volts. Once you've found that point, a white china marker may be used to mark the spot. Then locate another point nearby where the voltage is also 2.0 volts and mark this spot as well. Continue in this way until a number of points are located. The string of white dots forms an equipotential line and should be connected with a smooth line. You'll notice that our 2-volt equipotential line wandered considerably from the expected course because of our loose wing nut. You will be more careful, I'm sure. Continue in this way, constructing equipotential lines for 3 volts, 4 volts, etc. through 8 volts. Once you have constructed a complete set of equipotential lines, you may use a red marker to sketch the perpendicular electric field lines. Be sure to include arrows to show the line direction. We repeat the experiment with the high and low voltages attached to single points. This is similar to an electric dipole with positive and negative charges nearby. The holes in the paper must be along the x-axis at the points marked x equals plus or minus 8. As before, set the voltage to precisely 10 volts. Now the equipotential lines either wrap around one of the points or curve their way off the paper. Label the various voltage levels. Use the red marker to carefully sketch electric field lines. Remember, they begin at the high voltage point, end at the low voltage point, and are everywhere perpendicular to the equipotential lines. Place arrows indicating the direction of force on a positive test charge. Every good hiker also needs a compass. We'll use a small compass to sketch the magnetic field in the vicinity of an approximately dipole magnet. By definition, magnetic field lines point in the direction that the north point of a compass points. Place the magnet sideways in the elongated hole in the drawing board. Create a similarly shaped hole in a fresh sheet of paper and place it over the magnet. Tape the paper in place. Once you've begun sketching, do not change the orientation of either the magnet or the paper. The magnet orientation needs to remain fixed relative to the Earth's field. Place the small compass near the magnet and use the pencil to place a dot where the red compass arrow, that is the north end, points. Move the south, silvered end of the compass to the previously marked dot and place a new dot at the red end. Continue stepping outward in this fashion until the line of dots either wraps back around to the magnet or leaves the page. Connect the dots with a smooth curve. Begin again with the compass near the magnet in a new location. After completing several of these lines with judicious beginning points, the magnetic field will have been plotted over the entire page. Be sure to include arrows indicating the direction that the north end of the compass is pointing.